Aristotle, Galileo, Newton, Utah's Senator Jake Garn, and you, all subject to inertia and gravity, the basic laws of nature, this time on Science Without Walls. We're learning to think like physicists, to discover and understand the basic forces and energies which govern and control our natural world. Last time, we unencumbered ourselves from instruments, devices, and preconceptions. We relaxed, observed, asked questions. We appeared to be on a huge, flat, stationary object with a magical sun, moon, and stars essentially rotating around us, or at least passing overhead. We came to the same understandings and conclusions as Aristotle some 2,000 plus years ago. The earth is privileged. It's the center of things. Aristotle was really the first physicist. Although he and the Ionians before him were deeply immersed in civilization, science was not yet very well developed. Aristotle concluded that the earth world, which he called the sublunar world, is very different from the heavenly world, the celestial world of the stars and the sun. He felt very comfortable in attributing certain mechanisms and actions to the heavenly world, and very different ones to the earthbound or sublunar world. He said there were three different types of motion: natural motion, or falling, the tendency for objects to fall vertically to the ground; horizontal motion, which he defined as violent motion, because you needed to push or apply force to an object to make it move. These were the two sublunar or earthbound motions. And then, of course, there was celestial motion. This was different, perfect, and due to different forces. And of course, the heavenly bodies rotated around the earth in perfectly circular paths. Aristotle looked at things from the point of view of air, earth, fire, and water. His names for matter, that's air, water, and earth, and energy, fire. This was the basic understanding of the physical world for literally thousands of years, and is still the belief of the majority of our population. Most people's beliefs and understanding of the physical world are really Aristotelian. Then, in the early 1500s, along comes Copernicus. He concluded that things only make astronomical sense if the earth revolves around the sun. He developed the heliocentric theory of the solar system, helio for sun. But the intellectual, cultural, and religious inertia of the time were so strong and so well developed, and the separation between heavenly and earthly actions and activities so well entrenched, that Copernicus wisely did not try to publish or get much press until his death. His life's work on the revolutions of the heavenly spheres was published in 1543, on the very day he died. His embarrassed editor argued that the work was not to be considered a real picture of the way things were, but merely a model or simulation for the purposes of making calculations, perhaps for navigation and other things. So the book was tolerated and perhaps even used, but did not lead to a paradigm shift. Then along came Kepler and Galileo. Kepler really wanted the sun and the planets to rotate around the earth, but using new and very accurate astronomical data, he realized that things just wouldn't fit, and he finally became a heliocentrarian. More or less contemporary with him was Galileo. Galileo had a great advantage. He was an astronomer, a celestial physicist, and he was an earth physicist, interested in the forces and energies which govern motion on Earth. He also had access to the telescope, developed in the early 1600s and used by ship's captains for sighting land and other ships. Galileo not only turned his telescope to the heavens, but figured out ways to significantly improve and enhance it. He also took Aristotle's views and observations, dealing with falling motion and horizontal motion, and tried to make some sense of that for himself. He knew that the earthly motions were somehow combined. Thrown balls and projectiles obviously move horizontally and vertically. We say they have horizontal and vertical components to their motion. So Galileo did what scientists since have tried to do. He simplified the system. He idealized the problem. He made a model so he could deal with it and eventually understand it. It was hard to measure seconds and milliseconds very accurately back then. So Galileo tried to slow down the vertical motion by using inclined planes, like in this game, with tilted flat surfaces. High tilt, fast motion. Slight tilt, slow motion. No tilt, no motion. He also realized that there was friction which plagued, contaminated, and complicated his observations. He realized that it was friction that had confused Aristotle in his studies of horizontal motion. So, he used nice, smooth, hard, rigid, inclined planes, and smooth, rigid, and perfectly spherical balls. He also slowed down the vertical motion so that he could make accurate time and distance measurements. Remember, scientists like to count and measure. Until you can count and measure something, your knowledge of it is very qualitative and therefore really subjective. It's numbers which allow you to do things objectively. So by minimizing friction and using a slight tilt, he set up the experiments so that the ball took some time to get to the bottom, allowing more accurate measurements. Galileo quickly learned that if you allow objects to roll downhill, even on the slightest slope, they not only roll, they accelerate. Their velocity increases with time. He did the thought experiment. If a ball is launched horizontally on a perfectly frictionless surface, then there is no acceleration or deceleration. There is no mechanism, no force to stop it. It finally stops in real life, like this toy car, because of air resistance and because there is friction between the car and the surface. You know air forces and friction from personal experience and the effect of streamlining on wind resistance. You also know surface friction from personal experience. So Galileo got rid of friction, both air friction and surface friction. And by getting rid of friction, he discovered Newton's first law of motion, the law of inertia. If things are moving, they keep moving, or if they're stopped, they stay stopped. The books are not moving, and they're still not moving. That's inertia. We applied a force to the paper, moving it, but there wasn't enough friction for that force to connect to the pile of books, so the books did not move. In doing these experiments, Galileo applied a very important principle of physics. Complex motions can be separated into their component parts. For example, in the inclined plane experiments, there's horizontal motion and there's vertical motion. You can experiment with, sort out, understand each part, and then put them back together and get the real world motion back. From complexity to simplicity, then back to complexity. It's the way most scientists work. Physicists and engineers separate complex systems into their component parts, try to understand each component, and then put the parts back together again. We call it separation and then superposition, or putting back together. We need some definitions. First, average velocity. It's the distance you traveled divided by the time it took you to get there. Typical velocity units are meters per second or miles per hour. Galileo observed that the velocity of falling objects increased linearly with time. We call an increase in speed or velocity with time acceleration. When you press down on your car's accelerator pedal, you accelerate. Your velocity increases. So Galileo observed that the velocity of a falling ball was increasing, but it increased, it changed at a constant rate. It had a constant acceleration. We'll see this in just a minute. What was a bit surprising was that it didn't matter how heavy that falling object was. The vertical acceleration was always the same. Aristotle didn't recognize this because he, like you and I, did not separate the effect of friction. Friction's another force. Generally, more massive objects are smaller than less massive ones. Bigger objects have a greater area. Remember, the greater the area, the greater the air or wind resistance. And air or wind resistance is just another force acting on the object. When you stick your hand out of a car moving 30 miles an hour and you rotate your hand, you immediately feel that wind resistance. If you go a lot faster, say 60 miles an hour, that wind resistance is stronger, much more than twice as strong. Air resistance scales non-linearly with velocity or speed. So air resistance is very important in the study of falling objects and projectiles. Galileo recognized that and designed experiments where that complication was minimized and could be ignored, allowing him to discover Newton's second law of motion, which relates force, acceleration, and gravity. We'll see how in just a minute. So Galileo really did discover both inertia and gravity, although he didn't develop those concepts with the mathematical elegance that Newton later did. So we attribute those concepts and those laws of motion primarily to Newton. Here's a key Galileo experiment using a modern video camera. As the ball falls, the video camera records its motion. Remember, the video cameras work by taking 30 static images, one right after the other, every second. When these are played back, your eye fuses those images into a continuous dynamic image. We saw that the individual static images are there on the videotape when we use the jog key on a modern VCR back in Program 2. In order to see the position of the ball as a function of time, we'll view the ball from far away and record the entire 5-meter drop. Behind the ball is an enormous 5-meter scale, so you can see the position of the ball in each frame. There's the ball, there's the scale, position 0. The ball isn't moving yet. When we release it, it will move very slowly and then move faster and faster. Watch. Here we go. Bingo, it's all over in a second. But we have the data in the video camera, recorded at 30 frames per second. Now using the jog key on our VCR, we can see each individual 1/30th of a second image. And we can make distance measurements on each individual frame. Here's the result of the ball falling. The time between each ball image is exactly the same and based on the frame rate of the video camera. The distance increases because the ball is going faster and faster. Now we measure the distance the ball has fallen as a function of time or frame number and plot it. The distance graph curves upward. The ball is going faster and faster with each unit of time, covering a greater and greater total distance. Well, distance divided by time is velocity. So we can calculate the velocity at each specific point on that graph. And it is the slope, m, at that particular point. Now we plot that velocity that we've just calculated as a function of time. And that new graph is approximately linear. The velocity is linear with time. The ball's velocity increased by the same amount as we went from frame to frame. And the slope of that curve, the change in the velocity in an increment of time, is the acceleration. And its value? 9.8 meters per second per second. That's about 30 feet per second per second. The acceleration of that ball towards the center of the Earth is a constant. Good work. But we need one more experiment to really get to the bottom line. Let's take a heavier ball. This one is nearly 3 times the mass. It's the same size and surface texture, so the air resistance of the 2 balls is nearly the same. We'll now do the same experiment. Here it is. We do the same thing with the individual video frames, separating them and measuring them. And now we'll put the 2 sets of data, those of the heavy ball and of the light ball, alongside each other. Amazing! The 2 balls fall at the same rate, the same acceleration. Incredible? No, that's just how the world works. The acceleration due to gravity on Earth is a constant. The precise value, of course, depends on your elevation with respect to the center of the Earth, and so it varies slightly from point to point. But generally, it's 9.8 meters per second every second. Let's say 10 meters per second, with every second of vertical acceleration. Just what we observe. And that's good work. The effect you get when 2 things seem to fall at different rates, like a ball and a feather, is all due to air resistance, not to gravity. And thanks to Newton, we now understand that. These experiments used to be hard to do because vertical motion is so fast. But now we have video cameras and other instruments to help us. Galileo didn't have a video or high-speed camera, so he had to slow it all down with inclined planes. Gravity is what physicists call a very long-range force. The radius of the Earth is about 6,000 kilometers. The breathable atmosphere thins out with altitude to roughly 10 kilometers, no more than the height of Mount Everest. And then it gets thinner and thinner, out another 90 kilometers or so. And that's really where space begins, about 100 kilometers out. No atmosphere. Satellites generally orbit above that. So for all of us here on the planet, our distance from the center of the Earth is roughly 6,000 kilometers, making the acceleration due to gravity on the surface of the Earth a constant. If you were 60,000 kilometers away from Earth, about 1/6 of the distance to the Moon, you still feel the tug of the Earth. You still feel gravity. But it's only about 1% of what it would be here on Earth. That may seem like a small amount, but it's very significant because there are no other forces out there to compete with gravity. Even a very small force can be significant if there's nothing else around to counterbalance or counteract it. We'll see later that's really how the solar system is held in balance. Let's consider so-called weightlessness for a minute. The general conception is that Senator Garn and the other astronauts who were in the space shuttle were completely weightless, that they were far enough from the Earth that they were not attracted by its gravity. Well, based on what I said a few seconds ago, you should question that. The shuttle astronauts had almost the same gravitational attraction as you and I do here on Earth. They aren't really very far up. The difference is they are in a space shuttle, which itself is falling towards the center of the Earth. And the astronauts are also falling with the same acceleration. If what's around you is falling at the same rate as you are, you sense, experience, feel weightlessness. Weightlessness is when you are not pushed against various walls or surfaces. And that's the case if those walls or surfaces are moving as fast as you are. So Senator Garn and the other astronauts were certainly influenced and attracted by the Earth's gravity, but so was the space shuttle. And the result was that they appeared to float free. If they had not both been attracted by the Earth's gravity, their orbital velocity would have taken them out to outer space and beyond, and we'd have lost both the shuttle and even Senator Garn. We'll consider losing the senator again in another minute. Newton was born in 1642, a year after Galileo died. Newton got the credit for some of what Galileo did because Newton was able to mentally turn off gravity. Things aren't so obvious here on Earth because of the tremendous influence of gravity on all things. Imagine if we could switch off the force of gravity. You would no longer be pinned to the planet. All the air in the atmosphere would leak away to outer space. There would be no air resistance. There would be no friction between you and the road or the sidewalk because there's no gravitational force holding you to that road or sidewalk. You would then really feel and know inertia. You would be a mass with no gravity acting on you, traveling in a straight line. There are some times and conditions in which you can partially experience that here on Earth, even with gravity turned on. Hitting a patch of black ice, a situation of ultra-low friction between you and the road. You and your car then move in a straight line because there is no way you can impose frictional forces. You are subject to inertia, moving in a straight line at a constant velocity. Newton understood that gravity is caused by an attraction between two masses, although he had no idea why those two masses attract, and neither do we. The bigger the masses involved, the greater the force of gravitational attraction. By making observations of the Earth-Moon system, Newton came up with an equation to quantitate the force of gravity. The force between two objects is found by multiplying the two masses and dividing by the distance squared. We won't worry about exactly how he derived that, or how he figured out the mass of the Earth, m2, or that its radius is 6,000 kilometers. But now having such an equation for gravitational forces, and knowing the mass of the Earth, m2, and knowing that we are roughly 6,000 kilometers from its center, we can derive a similar equation, and that says F equals mg, where m is your mass, or mine, and g is all this other stuff. We call g the acceleration due to Earth's gravity. And whether you have a mass of 50 kilograms or 200 kilograms, the acceleration due to gravity is the same, g, because it's dependent only on the mass of the Earth and its diameter. When you weigh yourself, you're not measuring your mass. You're measuring the attractive force between you and the Earth. Your weight is the force of attraction, the gravity force, between you and the Earth. Newton could mentally turn off gravity, and he could turn it back on. He understood inertia, and he understood gravity. And then it sort of came to him. One of those creative, brilliant insights. What if the Earth behaves like a ball on a string? The ball would like to travel in a straight line, but is constrained by the string. So here's a model Earth on a string. The globe is tethered by the string. Watch carefully. It's a projectile moving in a straight line. What held the globe in orbit was the force on the string, the centripetal force. Well, Newton thought, what if gravity provides that centripetal force, and it just happens to perfectly balance the inertial tendency, maintaining that ball, or the Earth, in a near circular orbit. And that's exactly how our solar system is balanced. This may all seem simple by hindsight, but everything is simple by hindsight. It was brilliant. What it didn't answer was who or what launched the planets in the first place, a question we won't consider here. But given that the planets have a velocity and a mass, they have inertia, and they have a gravitational attraction to the Sun and to the other planets. And those tendencies are just balanced. So the planets are in near circular and stable orbits around the Sun. If you could turn off the gravitational attraction of the Sun, the Earth would simply coast, move in a straight line through space, just as it did when we let go of it as a whirling globe. So let's now retrieve Senator Garn. His space shuttle in its orbit is also constantly falling towards the Earth. What keeps it in orbit is that the NASA scientists and engineers figured out just the right orbital velocity to counter its attraction to the center of the planet, resulting in a stable orbit. The shuttle is actually coasting around the Earth, just as the Earth coasts around the Sun. And fortunately, Senator Garn did not careen into outer space. Well, we're out of time. In the last half hour, you've developed the Newtonian Galileo concepts of inertia and gravity, balanced the solar system, and moved way beyond Aristotelian 2,000-year-old physics to Newtonian physics and the mechanical view of things. Good work. Next time we'll finish up Newton's laws of motion, and we'll start to deal with energy and with that wonderful concept called entropy. We'll see you then.
It's a long, long road from which there is no return. While we're on the way to there, why not share? He ain't heavy, he's my brother. He's my